We're going to continue talking about piezoelectric materials, and last time, as you remember, I introduced some quantity called the dipole moment, or which we also practically call the polarization or the spontaneous polarization. And in the material, we draw this arrow inside of a material just to denote which direction it is, and I'll be explaining why is it important to understand that with regards to material properties and the behavior of the material with regards to a stress or with regards to an electric field. The simple explanation of piezoelectricity, is that we apply a force and we get out charge. So essentially, we're converting force, which is a mechanical force, to an electrical type of energy, which is in this form is charge. Or on the other hand, we can apply an electric field to a piezoelectric material, and we can get displacement So it's because of this type of interaction we can go from mechanical to electrical, or in this case, electrical to mechanical. So we can go back and forth between these two types of energies. And this makes piezoelectric materials known as a smart material. And this is because there is a coupling between the material properties of mechanical and electrical and mechanical. Normally, for example, a so-called dumb material property would be thermal expansion. So we have a material, we know that typically when you heat materials up, they expand, right? They expand if you increase the temperature. But if you expand them, now instead, if you just pull on it, will the temperature increase? Will the opposite thing happen? So in this case, we increase the temperature, and then it expanded. And in this case, where we're pulling it, will the temperature increase? No. This is why it's not a smart material, because these material properties don't go both ways. It only goes one way. So again, we have this material with a polarization direction, which we'll just typically draw as that. And I mentioned that if we introduce a force on a piezoelectric material, we're going to get charge. And this is simply denoted as P equals the stress times the piezoelectric D constant. So this is the thing which is going to allow us to model piezoelectricity in a material and couple the electrical and mechanical behaviors of the system. So in this case, we have polarization equal to the stress times the piezoelectric D constant. So the easy way to kind of get a feeling for this is that we apply a stress, and through this piezoelectric D constant, it tells us how much polarization we have. In polarization, the units of which are coulombs per meter squared. So we understand that we're getting some charge appearing on the surface. So we apply a force and we get charges appearing on the surface because of that. Now, this is called piezoelectricity, force, which is piezo, electricity, and then which is the electric charge, which is going to result from that. And now the question arises, now, is this side negative and this side positive, or this side positive and the other side negative? Well, how do I decide which is positive charges and which is negative charges? And we'll be getting to that pretty soon. So what happens when you introduce a force on a material? So we have a piezoelectric material with a polarization like this. And then we pull on it, introducing a stress with some certain stress. So tension is known as a positive stress. So we have a positive stress applied to the piezoelectric material. And as I mentioned that in a piezoelectric material we're going to have a positive and negative, sometimes separation. I mentioned there's the dipole moment is caused by separation of the center of positive and negative charges within the material. So when we're pulling on it, what we're actually doing is we're increasing the dipole moment, right? We're further making these positive charges go up, and we're further making these negative charges go down. So we're basically separating them. And because we're separating them, we're increasing the dipole moment even further. The dipole moment is increasing. But to counter this increase in the dipole moment, we generate a reverse field, because there needs to be charge balance, because now charge is in balance. So the material wants to balance out the charges. So in order to do that, it develops a positive charge here and negative charges here. See, the negative charge is getting farther down, and the positive charges are developing on the top. And this sort of creates an electric field going down, which kind of counteracts this increase in the dipole moment. So we have that equation that we mentioned, P equals the dx. Another way we can write it is multiplying both sides by the area. If you did that by the area of the electrode, see, this is the electrode on the top and bottom, multiplying both sides, top and bottom, by the electrode area. So we have the charge then, because the polarization equals the charge times the area. There's many definitions you can write for this, but we'll use that for now. The charge times the area, so we multiply each side by the charge, and this equals force. So pretty much from this equation, you can very easily tell that, okay, you apply force and you get a certain amount of charge, and this is known as the piezoelectric D constant. And how do we determine which side develops the negative charges and which side develops the positive charges? Well, the way to know that is you simply look at, well, how is the dipole growing or is it shrinking? If the dipole grows, i.e. we are applying a tension force, we're further separating the positive and negative charges, increasing the dipole, we're going to get a reverse field. We're going to get a reverse field effect due to this increase. So we're going to need some positive, a reverse field is generated. Similarly, let's say we have the case where we are applying we're applying an electric field to the piezoelectric material, and we put electrodes on the top and bottom. You'll notice this in piezoelectric materials. We have electrodes on the top and bottom of the material. This is the polarization direction. And the reason for this is that we can get the entire surface to be at one potential. This way we can get a uniform electric field across the material. So we get a uniform electric field across the top and surface bottom, and it makes devices practical and easy to fabricate and use. So when we are this time applying an electric field, how do we do that? We apply a certain voltage. We apply voltage across the two surfaces. Therefore, an electric field is generated within the material with regards to how thick the distance between the electrodes are and the piezoelectric material. And we generate a displacement this time, which we can see as strain. And this equation is used for actuation. So we can tell, look, we apply an electric field, how much do we expect the material to expand and move? Mainly for actuator purposes. So we have the strain, the piezoelectric D constant, or the charge constant, and multiplied by the electric field. And this is the same exact constant which we just saw earlier in this equation. So it's kind of interesting that these completely couple, and the same property is used for both cases. So now, if you want to know, in actual terms, what's happening, we want to look at real parameters. So we look at the change in length times the length, or the height, or the length, whatever you want to call it, equals the piezoelectric D constant times the voltage times the height, or the voltage times the length, or divided by the length. And as you see, these cancel, and we get the displacement equals the D times the voltage of the material. And this gives us, again, the piezoelectric charge constant. It also gives us the change in length with regards to the voltage applied. And now, how do we know, again, does the material expand or shrink? Because obviously if you applied an opposite field, just like if you applied an opposite stress, tension instead of compression, or compression instead of tension, you apply a positive electric field with regards to the material, or negative electric field, what do we expect to happen? So let's draw this picture again on this page. So we have a piezoelectric material, and we said this polarization is this way. So again, we had this negative to positive, and when we apply an electric field, let's say this is a surface which is 5 volts, this is 0 volts, or ground. What direction is electric field? From negative to positive, or the lower potential to the higher potential. In this case, you are bringing the you are applying an electric field opposite to the dipole. Therefore, the material is actually shrinking in size. So when you apply it opposite, the material gets smaller. And when you apply an electric field parallel, let's say 5 volts to 0 volts, we're getting a change in L is positive. And here, change in L is negative. So by applying an electric field in the direction of the polarization direction, we are increasing the potential. Well, rather, we're increasing the length, or we're creating displacement in the direction of the polarization. And this is because when we reach this point, this charge right here is actually displacing this way. So with regards to the negative field, we have we have these negative charges, and these negative charges on this side, created by this potential, and this is a positive potential relative. This is positive, this is positive, this is positive. So what happens is the negative charges want to go to the positive side, and the positive charges want to go to the negative side. Therefore, these displace, and they become bigger, and the material becomes bigger. And similarly, when we have, so let's just draw it in 2D picture. We have a negative, let's say we have a positive charge, positive applied charge. This is a 0.5 volts, and this could be 0 volts. It doesn't have to be negative, this has to be relatively lower. We say this spontaneous polarization direction is this way. That means we have a positive charge here, negative charge here. Negative charges want to move to the positive side, positive charges want to move to the negative side. So basically, a electric field, this electric field right here, applied along the polarization direction, is going to lead to a positive strain. So this is relative to the polarization. If we apply an electric field that is negative, which is going to be opposite to the polarization direction, we will get a negative strain here. So basically, by applying opposite pressures and opposite electric fields, we can either expand the material or contract the material. I'll review this very quickly in the next video.